Okay, any questions as we get started? Anything at all?
What are the winning lottery numbers?
Yes, you could write a machine learning algorithm for that. I just was told that the grading of homework 2 is just finished, so I will, when I get a second, I'll post those on Canvas, so you should be able to see those today, tomorrow. And hopefully homework 3 is going well. And everybody started it. Hopefully it's a little bit fun, just the things you get to do there, and kind of some of the fun things that we've looked at in computer vision using neural networks. Let's see. All right, so we'll get going then. So this is going to be the part 2 on these recurrent neural networks. We're going to talk about. We're going to continue where we left off. We're going to look at some of the ways that just recurrent neural networks are used to do some of the things that we've seen in this class already, and then we're going to look at a kind of recurrent neural network that's like, if you see a recurrent neural network these days, it's almost always one of these. It's called an LSTM, which is the abbreviation for long short-term memory. And this is an important architecture. Again, still used. I was reviewing papers for iClear just recently. They were due yesterday, and there were some LSTMs in one of the papers. It was a baseline model. It wasn't like state-of-the-art model, but still they were there. So it's good to know these things. All right. So remember last time I kind of talked about like the sort of more general view of how to think about how inputs, neural networks allow you to have different kinds of inputs and outputs, not just of type, but of like different kind of sequential versions of the input and output, and how those might be arranged, and what types of tasks they would be good for. We looked at how you can think about a recurrent neural network as being a single cell that keeps updating itself as you move through the sequence. But if you think about the computation graph, you need to do what's called unrolling that. So like for each step in the sequence, there really is, even if it's shared weights, there's another node in the computation graph, and that you need to back propagate through all of that. We talked about how to make that more efficient by truncating it, and we looked at some examples. So we're gonna look at some more examples here. This is kind of fun. So again, taking pretty standard recurrent neural networks, trained on text of some kind, language, or code. We'll see some examples in code. We're gonna think about. We're gonna look at the cells in a recurrent neural network, and we're going to see which of those. We're going to see if any of those sort of like have learned something that we can interpret. It's a little bit like being a neuroscientist. We're going to look at, think of these as like neurons. We're going to look in there, and again, like we did for computer vision, where we were looking, when we were thinking about visualizing or interpreting what convolutional neural networks were doing, we did this thing where we looked at all the examples that say were produced very high activations for a particular neuron, and we saw that like deep in the network that gave us there was like a lot of visual characteristics that were similar between those images. And so we're going to do something kind of similar to that here, but we're going to look at text instead and see if we can learn some things. So we're going to be looking for this unrolled computation graph. We're going to be looking at some of these and see if they get large activations or negative activation, large negative activations for particular types of text input. So what does that even mean? Well, what you can do is as you input texts in a trained recurrent neural network, you can look to see again, if what the level of the activations are. So we have a heat map here. This is for one neuron or one cell in the recurrent neural network, and it's a heat map in the sense that if it's very red, this is a very large activation. If it's very blue, it's a very negative activation. If it's it's white, then it's neither, right? It's like, close to 0. And remember here, what's interesting is that it's not just like we have the heat map on a particular letter, but remember, this is already, all of this has basically come before it, right? All the rest of the text in front of it has come before it. So the state of the recurrent neural network has been building up, up to, like, say, this point. If I pick out this F right here. And so it's not just that, like, whatever this activation here, it's not just that an F showed up here and it's, it's not very activated. It's that an F shows up here and then all this other stuff occurred, before it, right? And so if we start looking at the patterns of these things, we might be able to look at these and say, oh, look, this neuron learned, this cell learned, like this kind of interpretable information about the text. So this is not a good example. This is like, who knows what this is doing. This is probably what most of the recurrent modules or recurrent cells, like this is like their activations, this is what they look like. But some actually are very, very structured, which is really cool. So here's an example of one where, see how this starts with the paragraph here starts with a quote. And the quote it's white, so this is like neutral activation. But as soon as you enter, you look at the text after that, it appears that everything after that has this very like low activation, right? So that's why it's in blue, very like negative activation. And it stays that way until what happens? We get to another quote, and then all of a sudden it changes, and now we have very high activation for this particular cell. And so you keep going, You might think this had to do something with the fact that the quote showed up at the beginning of the paragraph, but if we look at another example where the quote's kind of in the middle of the paragraph, you get some kind of similar behavior where, once the quote has neutral activation and then, this blue or low activation until we get to another quote. So this is interesting, right? So remember, this is just trained on examples of text. So this doesn't really know anything about like what quotes are about. But what does this thing learn to do? What's that?
Identify quoted text.
Yeah, what this thing is basically keeping the state of like whether the text is in a quote, a double quote, or not, right? And why is that useful? Well, apparently this is super useful because quotes come in, the quotation marks come in pairs, right? Like they always do, and they need to like end at some point. So you need to have some way of kind of keeping track of where you're at there, and then eventually kind of produce the signal that's going to end it, right, and give you the closing quote. So remember, again, these RNNs, these character RNNs that are just trained to produce the next character given the sequence of characters previous to it, it's found it advantageous to be able to track at a high level whether or not we're within a quote block or not. So that's pretty cool. It's just emergent behavior, right? So this isn't a rule that we gave it. It just learned to do this because this was useful for producing text that looks like the text it was trained on. So that's pretty cool. What else can you find in here? Well, they found all sorts of cool stuff. So this is interesting. You have another cell that seems to have this gradient from like very blue to very to very red activation as something is happening here. And what is it? Well, in this particular case, it looks like it is the length of the line or like the position of the line. So it's somehow keeping track of, somehow doing some kind of counting. Like once we get to the end of the line, so like so if you think about it, this was trained in such a way as to produce like new line characters, right? So it's gotta like put a new line character in to start the new line. So it's basically saying like, I'm guessing, I actually don't know it for sure, but I'm guessing that the text was formatted in such a way that you had these, you had like a hard wrap rule where if you you can have, I don't know, what is it, like 120 characters or something like that, who knows exactly. But that, and after that it should wrap, and then so you have a new line character, breaking between the spaces, and then go to the next line. And so there is something that's, there's something in the network that's keeping track of that state. So it knows when to produce a new line character, right? So like this is just saying, like, we know what it's like to be text like this. You can't, these things can't be too short, these can't be too long. So like let's have something that more or less keeps track of that. And then that, basically you think of like the network as integrating all these different signals, and when it sees this particular cell being very active, it's like, okay, we now need to generate the new line character. Again, this is not like a rule that's programmed into it. It's just because it's a strong characteristic of the data it was trained on, the text it was trained on. It's learned, it's, in order to do that, it seems to have learned to keep that state in one of the cells. Yeah.
So,
go ahead. Yeah.
Was that, so it's not doing an exact count, which you can kind of see when you look at the third to last and fourth to last line. Like they look like there's these bridges and children there at the end. They're different colors of red, even though they're both clearly the same length. I guess I'm still confused. So it's not keeping track of the count, but it's keeping track of an approximate count. Is that kind of what we're looking at?
Yeah, I mean, it's hard to know exactly what it's doing, because like almost surely it's not counting. That's like a discrete operation, and these things are very continuous. They're actually, they're differentiable. So if you remember your math, if you have differentiable functions, they're continuous everywhere, right? So yeah, like it's not doing something like that, but it does have some capability of just being able to say like, oh my goodness, this is getting really, really long. Like you better put a new line character in there fast, right? Like it very rapidly goes from from blue to like deep red, so that it's giving that signal. So it's hard to say, like it's hard to say that this is exactly like a line, or a character counter for the lines, but it's clearly tracking something like that as part of the state.
Like you think, for example, like the when the bridges line, it has a lot of little words inside of it, whereas the one beneath it has a lot of big words inside of it. That might have contributed to it.
Yeah. I mean,
it's keeping track of multiple.
But remember, it only has access to the state. Like the state only has access to what's come before, not what has come after. Yeah. Anyways, so that's kind of interesting, something like that. What other things? So like now let's look at this is trained on something else. It's trained on, again, like this is probably the Linux source code again. What does this have in there? What's something you would see all the time in, well, pretty much any any imperative code here. You've got conditional expressions. You've got these and being there's clear structure to them, right? There's if, there's the condition, and then there's like the expression of the condition. And so when you're training this, there appears to be something that's keeping track of when you enter into the condition of the if statement in this case, and then like what follows, and of course if what follows starts with an if, then we keep track of that, and we kind of like recurse in, and then kind of return back out. So again, in order, it's found it useful in order to produce text in this case that looks like the Linux kernel or Linux source code, that it keeps track of things like this. Now, it's all just kind of like a party trick in some sense, right? This is not like, again, there's like no one programmed these rules in, and really like you had to go through and like carefully keep track of, like look at each of the neurons in these networks and say, okay, like is this tracking something interesting? I don't know. Like let's look at a bunch of examples of it, like in these heat maps, and then every once in a while, like one of them shows some interpretable patterns. Most of them are going to be like that first one that we showed, where like it doesn't seem to be an interpretable pattern, and it's more like an integration of all of that signal together to produce the next, the next character in the sequence. But the fact that every once in a while there is something, interpretable is kind of cool and interesting. Yeah, there's other examples. Here's one that's keeping track of being inside comments. Again, it's very similar to like the quote example, right? Where if you enter into a comment block, you know how it starts. You know that there's going to be something that ends it. You're just kind of keeping track of that state until it happens. Here's another interesting cell that's keeping track of the depth. You know, how far you kind of like you know, in some sense, kind of keeping track of the stack in which you are you're pushing onto here, just for different kinds of you know, procedural statements. So that's kind of cool. Great. So, anyways, you can play games like that for any kinds of text. Like again, it's mostly like a party trick. You know, you kind of just show up at, you know, party on Friday night and just like wow your new friends there with, hey, check out this neural network behavior, and then you're like obviously the coolest person at the party. But there's, you know, so maybe not super useful, but kind of interesting, and also like just in the same way that we use ideas like this in understanding computer vision. It's just some way of just thinking about what's being learned, even if it doesn't give us some, you know, even close to a complete description of what really is happening inside the network. Again, it's very hard to do that because of the nature of the computation being done by a very, you know, large model with many parameters. Okay, so now that we know something about recurrent neural networks, there's an example we've seen in this class a bunch of times: image captioning. Okay, so how does image captioning happen? Well, the way it happens is like this. You have a convolutional neural network that, you know, encodes your image into a vector, right? We've seen this a bunch of times, a bunch of different examples. That vector can be of, you know, various lengths, but it's whatever comes out of here is like some representation of the image here. Now, if we want to do captioning, well, what do? Well, the standard approach here is to now use that. Like, you want to condition a recurrent neural network on that representation, right? You want it to depend, like what you produce here, you want it to depend on what's in this image. And the way you do that is you simply feed this this representation of the image in as the initial hidden state of your recurrent neural network. And so now, when this thing goes to start, you know, learning to produce like the next, and we're no longer, in this example is no longer the next character, but like the next word. That hidden state now, as it starts to accumulate that, it's going to be, you know, it's going to depend, it's going, you know, we call it conditioned on that image, the content of that image. And you can train this whole thing end to end, you know, backpropagate this all the way through, just as we saw, you know, like in convolutional networks, but backpropagate this through the neural network and into here. Now, you don't always do that. You could do that. Oftentimes, this could be already just like a pre-trained convolutional network, and then you just learn the rest of these parameters here. But you could do the whole thing end to end, you know, if you wanted to. And the point is that this works, and this, you know, for the like data sets like COCO that have, you know, roughly 5 captions per image for hundreds of thousands of images. This ends up being a really excellent way to learn to like produce those captions, the captions of those images that we've seen over and over already as examples in this class. And it's really doing nothing more than combining these two architectures into one. The convolutional network to represent the image, and then the recurrent network to produce the caption. So that's pretty cool. Questions about that? Questions about how that works? Yeah.
So you're training both networks, the recurrent and the convolutional.
You could do it end to end, or very often what happens is that this is just some pre-trained convolutional network, and then so you can think of this as just as like a feature extractor, right? So it's a fixed feature extractor, and it produces some vector, you know, whatever length that represents this image. This weight matrix right here is a way of basically projecting the dimension of this representation into the correct dimension to be like the correct size to be a hidden input for the recurrent neural network. And you know, you could just be training end-to-end this, and then all of the typical weight matrices from a recurrent neural network. So you could do it end-to-end, but oftentimes that's not done that way because you have all these really excellent, like existing pre-trained image encoders, and you just use one of those, and it works completely fine. Yeah. Why does it work completely fine? Well, mainly because these things would have already been trained to do things like recognize that there was a straw hat, or a hat or something like that, right? So like the semantic content that's in this, that's encoded in this vector from this is already sort of related to the things, like the ways that we would caption anyways. If they were totally unrelated, like if the captioning was about like something like, like maybe like saying something about the size of the image, right? Like that wouldn't work, because of course the way that thing was pre-trained shouldn't have any information about that in it, right? So in that case, you'd probably want to train end to end, or like if sometimes there's recurrent neural networks have a hard time propagating a lot of signal back through the whole thing. So you might think about training this on do some pre-training on a task that is related to the captioning, and then fix it and do the next step. Good question. I think there's a question over here. Yeah.
So when you're using now words as tokens, do we still represent them as just like create one hot vectors, or is that things like labels?
Right. So it kind of depends on what you're doing. In this case, you can do either one. You can do either one. So if your vocabulary starts to get very large, which for captioning it might, right? You might have hundreds of thousands of words you're interested in using in your captions. Then you probably want to go to like a dense encoding from something like a word to vec, something that's already again pre-trained, but that will keep the dimensions. Instead of having like hundreds of thousands of dimensions with only a single number, you want to have just like a couple hundred dimensions. But instead of it being that sparse representation, it's a dense representation. And then here, you're just doing, this is literally, like whatever the size of your vocabulary is, this is, a classification task with hundreds of thousands of tokens in it.
Instead of using many for your output, you use one hot vectors?
I mean, your output, you can think of as one hot vectors. Yeah, like you can think of those labels in that way. But yeah, right. It's that's how like the typical cross entropy loss works, the multi-class cross entropy loss. So yeah, that's how that works. So yeah, if this ends up being very large, like you often will use a dense representation like word to vec to be the way that you get the initial representation of the tokens in your vocabulary. And there have to be other tokens in this vocabulary too. We haven't really talked much about this yet, but like we'll talk about this when we talk more about machine translation. But there needs to be, you need to know when to end these things, right? Like the phrases are a variable length, right? We can maybe say the same thing, but like in a couple different ways, and we might use more words one time, less words the other time. So how do you get around that in a system that like is expecting kind of things at fixed length? The way you do that is you add tokens, like an end token to say, we end the phrase here, and then we at training time we only train up to that point, and at test time once that appears, then we stop like producing tokens for the translate or like for the caption in this case. So you add there's a couple of special tokens in the vocabulary as well for that kind of thing, including like a start. And the start makes a lot of sense when you think about like translation as well, like the pairing up of phrases that should be translated into each other. Oh yeah, I've been saying all these things. So what does this look like? There's your pre-trained like VGG style network. You get the representation out. You don't go all the way to classification. You just use one of these representations. You produce your start token. You have your recurrent neural network. The conditioning of the network happens by passing a projected version of this representation of the image to the correct dimension as the initial hidden state, and then it's a recurrent neural network after that, and you hopefully get the right thing. And that's how this kind of work was done here. That's stuff that we've seen a bunch already as examples of like cool ways in which deep learning has really allowed us to do very, very interesting, often useful tasks that would be nearly impossible to do, like writing a procedural program. It's not perfect, obviously. Some things don't make sense, like that woman is not holding a cat in her hand, but you can sort of imagine why that happened. This person is not holding a computer mouse on a desk, but you can sort of imagine why that caption happened as well. There's no bird perched on this tree. Anyways, you can do some interesting things that we haven't quite we haven't really gotten into yet, but we're going to really rapidly get into when we start talking about attention. Especially next time, we'll get into some of the mechanics of what attention looks like, kind of where it first appeared, and then how it gets used in transformers. But kind of early on, one of the things that people were interested in was to say, so when we are, like, say, captioning an image, like, which pixels are helping us to do that, right? And we talked about saliency and those kinds of things that it was ways of highlighting pixels in your image that contributed to like the classification. So like which of the classes that the image had chosen. This is going to be something similar to that, but it's going to be more because we have a classification at every token for like what should be the next word. We can sort of do this sequentially, and so this looks very much like those saliency maps. The mechanics are slightly different, but what this is doing is highlighting, and you can, like, the lighter it is, those are the pixels that are being highlighted. The lighter it is, the more that those pixels are contributing to the production of the word underneath it in that caption. So you have kind of different versions of this: soft attention, hard attention. We won't kind of get into it. You can sort of see the difference though, that hard attention has a kind of threshold, where soft attention is more like this smooth gradient from low to high attention. But if you look at that, you can see like what are the pixels for the article A? Well, I don't know, like doesn't seem to be focused on much of anything other than like not the bird. But especially for soft attention, you have that the pixels are surrounding like the bird body and its wings seem to be highlighted. When it's flying, like it seems to be the kind of the same pixels, maybe like even a little bit more. Perhaps that's like the context of it being like in the air. Over, here's A again. You can see how that's quite a bit different, but you can see as we look at things that are more interpretable, like the water, it's interesting how if you compare this with say like bird or flying, the pixels that are used to make this produce a particular word seem to be everything but the bird. Like the water surrounding the bird in that original image. So it's kind of cool how you can get these networks to do things like use the pixels in interesting ways and have this tell you give you some idea of which pixels are important and how they produce this caption. You can see these for like different words in these examples. So in frisbee, you can see the frisbee is highlighted. For the word dog in that caption, you can see the dog is highlighted and so forth. I mean, this is interesting. Like here's giraffe standing in a forest of trees. I'm sure if we saw the example here with giraffe highlighted, like that's the word we're looking at, we'd see all the pixels in giraffe, but for the trees we see it surrounding the giraffe. So very intuitive. What other kinds of things can you do? Like we've used the example of like image captioning, but you can do lots of interesting problems here. One of the harder and more interesting problems here is this idea of question answering, or in this case like visual question answering. So you're given an image and then you're asked a question about the, like something about the image, and then you're asked to give an answer. And in this case, you can think of this in two ways. This could actually produce text that's the answer, but actually in this case, it's given, like a couple of different examples, like it's like a multiple choice question, and then it's asked, like which of these is correct. So again, that takes into, like, you have to be able to do things like encode, like the text here, so that can be used, in a kind of classification problem. Anyways, these kinds of problems can be approached in very similar ways, where you have a recurrent neural network that's conditioned on the image, and you train it to do, whatever associated text-like task. In this case, answer the question being asked. And actually, this is really cherry-picked. Like, this doesn't actually work very well. It still doesn't even really work that well, but it's getting much better. But it fails miserably in so many different ways. But the fact that you can even approach doing this and get a lot of sensible answers is actually quite amazing. We won't get deep into this. Just know that, like, the way that these things are done is and this is getting into what attention looks like, is that you have your convolutional feature map. So we conditioned the production of the sentence, whether it's the question or the answer, or whatever, on this image. The additional thing that we want to do is we want to be able to allow this to, when it's conditioning the production of the next word, to be able to allow this to up or down weight parts of the image as a learned operation. So basically, this is something like produce some of these weights for, this is a very coarse a coarse grid for that convolutional, not at every pixel necessarily, but like at patches of the image. Let it produce a weight, and then basically multiply the image by those weights, so that we can zero out a bunch of stuff, but then other things can maybe just be preserved or amplified or something like that, and have that then produce the input to the next, to be part of the hidden input for the next token. And then this is how these pictures that we've been looking at, like what's highlighted and what's not, is something like like this mask, like multiplying the image by some value, like between 0 and whatever, to show the highlighting here. We'll get more into this like next time, but it's it's interesting that this can be done. Okay, so let's think about this. So there are some problems with just the plain vanilla RNN, and we're going to look at this by just thinking about the gradients in an RNN, and thinking about just think about the operations and like how the gradients kind of flow through this. So this is again a kind of a plain vanilla RNN. This is like a sort of like state diagram for this. So you have, like if we're at position T in the sequence, we have our our input there, the T input, the token corresponding to that. We are combining that with the hidden state from the previous step. Those get combined. They get multiplied by some parameters W. There then is a nonlinear activation. In these early plain vanillas, it was tanh, and then that produces the hidden output for this particular state. So this is just kind of a simple way of visualizing this. And this whole thing about like stack and a single W is just because you can this like the way that we've written this up every time. You can think of this as stacking the two vectors, the hidden state from the previous step, and then the current input, stack them together as a single vector. We can also kind of not stack in this case, but like concatenate these two weight matrices. And this operation of this matrix vector multiplication, is equivalent to this. And that's what we're showing right here. But anyways, so like that's just like so the point of doing all this is that what a single plain vanilla RNN like forward step looks like is exactly like what we've seen in the past. It's a linear operation followed by a nonlinear activation. Okay. So not quite the problem with this. Just so recall what's happening here. When we're doing back propagation, we have, these things are all kind of lined up, from x, 1 through however many steps we were taking. And you think about what happens during back propagation is that we're moving back along all these lines from the hidden state here at t to the hidden state at t minus 1, back propagating that signal to adjust the w's, the weight at every step. So what's the problem with this? Well, the problem when it comes to gradients for RNNs is that we have the same w in each one of these steps, right? So that's a good thing on the one hand, because that has made this like a really efficient network to learn. We only have that one matrix to learn, through all of these different steps. Even though we're gonna, as we back propagate, we're gonna have gradient contributions to the changes in w from like each one of these steps. It's still it's w. And who knows their linear algebra? If you multiply by a matrix over and over and over again, what happens to that initial vector? Anybody know? Who knows anything about like eigenvectors and eigenvalues? Yeah? Okay, so what happens? Okay, so like, let's say we take an eigenvector and we multiply the matrix that's an eigenvector for. What happens? What do we get? So we have called x. So we have w times x. If that's an eigenvector, what do we get?
It's going to not change because of the linear transformation. It's going to part in the same
Yeah. Yeah, exactly. It's basically that the output of that lives in the same subspace spanned by that vector, meaning that it's going to be a scaled version of the vector. So it's lambda times that eigenvector, and that lambda is the eigenvalue. So let's do it again. Now we multiply again by w. So it's w squared times x. If that's an eigenvector, what does the output look like?
Lambda squared.
Lambda squared times x. So we multiply it n times. The output looks like lambda to the n times x. So what's happening as we continue to do this? Multiply by w.
Scale it.
It's just scaling it, and then what's happening to that scalar? It's getting bigger, is it? It depends. And what does it depend on? Yeah, it depends on the magnitude of lambda, of the eigenvalue, right? So if the magnitude is larger than 1, that's going to get larger and larger, right? You're think of it just like if it's a real number, you're just going to keep multiplying by a real number larger than 1 itself over and over. That's just going to blow up to infinity. And if it's the other way, if the magnitude of lambda is less than 1, it's going to converge to 0 as we iterate. So we do have the nonlinearities involved, so that kind of helps to break this up. But the nonlinearities can't sort of make the problems worse in some sense, because you're dampening in the branches of the tanh, you're dampening the gradient a bunch. But if we imagine that the parameters are such so that we stay kind of in the linear range of the tanh, then we just are getting this this forward pass is just multiplying by w over and over and over and over and over again. So even if you're not an eigenvector, if you know your linear algebra, you know that the eigenvectors of a well-behaved matrix like span the space, and you can write any vector as a linear combination of those eigenvectors. And then as you do this iteration, whichever vector has like the largest eigenvalue, that's going to be like the dominant behavior as you iterate. So what's happening is that if we think about this in terms of how this affects the gradients as we backpropagate through this, is that if we, by the way, I've been using eigenvectors and eigenvalues for non-square matrices. You have a similar concept called singular values, where the same behavior would apply. You just it's a little bit more general, but the reasoning is the same. If we're multiplying by many by w many times, if we have singular values or these eigenvalues that are larger than 1, our gradients are going to get very large. That's a problem. It's not the worst problem in the world because that's actually signal. But if that continues to grow unbounded, that just means we're going to be taking like huge steps, right? And if we don't somehow account for that, we're going to get really chaotic behavior. We're not going to converge. And then just kind of in reverse, if we have very small singular values, that gradient is going to vanish, meaning that like we're not going to be able to propagate that signal back, and we're not going to get enough learning, enough changing of the w's to really, get like converge to a good w in our space, in our parameter space. So that's the problem of vanishing gradients. So there are kind of like, I don't know, like ad hoc ways of dealing with that. How would one, what can you imagine like an ad hoc way of dealing with like large gradients? The direction's fine, like it's a gradient in a good direction.
Use some sort of like, I don't know, like large sigmoid function or something, just kind of like scrunch that a little bit.
Okay, yeah, like that. Yeah, the idea of scrunching it's a good one. Yeah, you could do something like that. You could even do something like much simpler, just like clip it. Those apply like a hard maximum. Like just don't. So like that's kind of what this would do, like in a smooth way. But you could also just like say, the gradients can't be like in magnitude any larger than 1 or some fixed value, and just clip it. This is super common, just in general in practical neural network training. But exploding gradients, you often just clip them. You just say you can't be larger than a certain size. It sort of feels like not good because it's not like it's just like this weird ad hoc thing that you're throwing on there, but it's practical and it tends to work. What about the vanishing gradient problem? What's a practical way of dealing with that? By the way, this code here, this is simply like, this is actually the square root of the norm. There should be a square root there. But this is simply, if the gradient's too large, we're gonna make this smaller than the threshold. We're gonna reduce it to the threshold. So often not just like chosen to be 1 or something like that. What about vanishing gradients? How can we fix that? Yeah.
Maybe you could keep track of like how many layers deep you are, and then multiply that by some number to that power.
Mm-hmm. Yeah, that's actually a really good idea. Like it could work. There's an interesting thing that happens. Well, that'll take me too far. Ask me about like half precision and things like that at some point. But yes, you could do that. It's a little bit tricky because like you have to kind of pay attention to where you are and things like that. Another really drastic thing that actually ends up being practical, but it's very very different, is to just change this architecture altogether. So what do we mean by that? Well, there's a lot of proposals for how to change this, but the one that seems to have like really sort of stuck, really sort of like been the architecture that is like the architecture that people use in this area for really robust recurrent neural networks, is something called the long short-term memory, or just LSTM. And importantly, this actually was proposed a long time ago, 1997. So way before the like deep learning revolution. And I don't know if anybody kind of knows the names here, but there's a name on there, Schmidhuber. Right? Anybody ever heard of Schmidhuber? But you've heard of like Jan LeCun and Jeff Hinton, and right. So Schmidhuber basically wrote a ton of papers with like at the same time that all those people were writing papers, you know, in like the same journals and things like that. But somehow he never got any recognition, and he's pretty mad about that. And if you like follow him on Twitter, like his whole Twitter's about like pretty much like every week there's like him like tweeting about a paper that he wrote in 1990 or something that's like the precursor to Transformers or something like that. And you know, so I don't know why history kind of happens the way it does, but he's been left out of like being like a key character in the development of modern neural networks. And here's a good example. Like he is one of the you know, he's one of the creators of LSTM, which again isn't it's not like it's a transformer or something like that, but it has been up until transformers like the model that people use, like the kind of state of the art for recurrent neural networks, sort of like sequential data. But yeah, if you're interested, go get on Twitter and like go find Jürgen Schmidhuber, and just you'll see he feels really slighted. There's a lot of memes and stuff too, but sort of unfair. I don't know, since I'm talking about names in history, Sept Hochreiter is interesting. He's the other, I think he was probably a student of Schmidhuber's, but he's gone on to have a really successful career, like published lots of really interesting papers, things like Hopfield networks that you might have seen, and actually is doing a ton of work in like drug discovery now, which is interesting. So the long arc of research. Anyways, so now that I've told you all the interesting history, what's the architecture look like? Well, remember this is our plain vanilla, right? It's this, we have a token for token represents the input, we have a token that represents the current state, like the previous state, and we're going to get the current state by just multiplying by a fixed parameter matrix, applying a nonlinear activation to get that updated hidden state. If you look at LSTMs, well, this looks the same. Again, we have some sort of, you know, matrix times things that we recognize. But then we have, who knows what's going on over here. This is kind of weird notation, but it's just basically saying like, we're going to apply kind of entry-wise a sigmoid, a sigmoid, a sigmoid, a tanh, that looks like this down here, and the corresponding outputs are going to be called I, F, O, and G. And how do we get to HT? Well, you notice it didn't show up over here at all. Well, HT is going to be some, whatever this O thing is right here, times tanh, it's not tanh of this right here, like it is over there, it's tanh of CT. Well, what is CT? Well, it's this thing right here, which is this I times G. By the way, this is like entry-wise multiplication, so that's what that symbol means. So you have this entry-wise I times G, this entry-wise F times CT minus 1, again, tracking some previous state. Add those all together, this gives you some like current state, but what is that? Well, it's like the thing that we use to then update the hidden state that then we recognize from what we saw in the plain vanilla RNN. So what the heck's going on here? What is all this? Well, it turns out this ends up being pretty interesting. And what's happening? Well, we're going to look at this in more detail. But just before we leave this page, you can sort of get a sense of what's happening. So we have, yeah, go ahead.
Are those sigmoid functions all different somehow?
No, that's just the sigmoid function.
So how is it producing 3 different variables if it's the same sigmoid function?
Right. So what's happening here is that we actually have this W is large enough to give us these outputs here. So we have different W's.
Okay, so we have
Yeah,
a
we're like
different-
learning. Yeah, so like we're learning different weight matrices for each of these operations.
I see.
Yeah. So it kind of gets hidden there, but so what's going on here? Well, this portion right here looks like what we had before. That's what this G is. Like that's what we had before, but somehow we weren't happy with that. We didn't like that. We needed to do something better. I mean, ostensibly we're fixing like the vanishing gradient problem. Well, how are we fixing it? Well, we have our G here. That's what should have been the hidden state. But now what we're doing is we're multiplying it by this I, and this I is going to be something that's whatever the vector is associated here. It's going to be we'll have applied a sigmoid to it entry-wise. So the entries of that are going to be somewhere between 0 and 1. So whatever was here in G, we're like scaling that by something between 0 and 1. So if these were all 1, this G would just be like this I entry-wise product times G. This would just be G. If these were all zeros, then this would be a 0. But more likely than not, we're going to have the entries of I are going to be somewhere between 0 and 1, and we're going to get some kind of scaling of the entries of G. Okay, you might think, all right, well we did some cool thing there. Maybe like that's all we needed to do, and we can just now have that be like instead of it going into the that could have just been the output. This kind of scale version of G. No, that wasn't good enough. What do we do? We're now keeping track of some other hidden state here where it's called C. It's called C. Oftentimes it's called for the cell state. And we're doing something similar, right? Again, we have whatever the previous cell state was. We're taking again something that's going to be a bunch of values between 0 and 1, a vector of entries between 0 and 1, and we're multiplying it entry-wise here, and we're integrating those two things here, and we're coming up with like some updated hidden state associated with that we're calling a C. These things have names. This is called these are called gates. I, F, and O. This is called the in gate. Again, like think of in as being like this is like our initial in, kind of like what was the output of the vanilla RNN. So like we're somehow gating that, right? Like the values of that are gated. If they're all 1s, the gate is fully open. If they're all 0s, the gate is fully closed. If it's something in between, like letting some signal in from G there. And then similar here, we have F. This is known as the forget gate, the forgetting gate. And the reason for that is that it's like this is it's multiplying by this previous like hidden state. We can forget this whole hidden state by having these be all 0s, or not by having these be all 1s, and then we integrate these things together and give the new thing. So we have the input gate, the forgetting gate, and then finally, whatever that state is, it now goes into a nonlinear activation, tanh, and gets multiplied one more time by another gate, O. What do you think this stands for? The out gate, exactly, output gate, and we get our final hidden state that we're keeping track of. So somehow one having to be able to gate the output of these like a plain vanilla RNN seems to be useful, and have this like this system where we have an internal state that we're like an additional internal hidden state that we're keeping track of before we produce the like true hidden state somehow is helpful as well. And how does this all look if we look at these like the computation graph or these kind of like information flow graphs? Oh yeah, this is so I always do this. I say everything that's on the next slide and I show you the next slide. I don't know what's wrong with me. Anyways, so yeah, this is basically everything I just said. But this is answering that question that you had before about the W's. There's different W's for each of the gates, and they're the name of the gates. Yeah, and G is not a gate. G's just input. Gate, whatever. But it's important to think of this in terms of like how how we're adjusting the internal states of the that we're keeping, the C and the H, right? We have like initial input, we gate that. We have like some intermediate hidden state, we gate that. That gives us our new intermediate hidden state. We then apply another nonlinearity and gate that, and that gives us our final output state. And somehow being able to do this is good and useful. Well, how? Why? Well, it has to do with this kind of crazy, computation graph. So some of this looks similar to what we saw before, right? Like, this looks very similar. Remember, keep in your mind, we are trying to deal with the vanishing gradient problem, right? Vanishing gradient problem happens because we're multiplying by the same matrix over and over and over again, and if all the eigenvalues have magnitude less than, or singular values have magnitude less than 1, then the signal is disappearing as we iterate. So we have that, great, whatever. Then it goes through all these kind of like these crazy gates, and somehow this all integrates into the output of our hidden state. But we have a secondary track here of information, input to output in this forward step. And notice how different this is right here. The flow of that information from CT minus 1 to CT. So there is a chance to gate it, meaning like multiplying by the entries by values between 0 and 1, and there's a chance to update it, and all this depends on all these gates depend on W. But notice that that the effect of that W is squashed to values between 0 and 1, right? So this is like not in there's like not a linear range here in which we're like multiplying the input. This is simply saying the way that we update in here, there's simple operations that depend on this state, but it isn't the case that we're multiplying by that matrix. And that's important because while this track right here still you still might say that, hey, we're multiplying ht minus 1 by a fixed matrix and getting out an ht, and we're doing it multiple times, and that gradient could vanish. This is not happening up here. We're not multiplying by a matrix up here. And when we backpropagate from the signal here, we backpropagate from CT to CT minus 1, there's a very direct what do you call this? Like this track, this backpropagation track from CT to CT minus 1 that doesn't pass through a matrix multiplication. And so whatever's happening to the H, whatever's happening to H here, I think if this wasn't happening here, we'd still be in the same kind of world of hurt in terms of the vanishing problem. But because we added in this intermediate state here, CT, we now, when we do backpropagation, we now have something that's not affected by like matrix multiplication. So what we expect is that this hidden state should be much easier to backpropagate information through C than it was to backpropagate it through H, through long, through many steps of the sequential data. Now, the exact details of this, like how they affect here, obviously they're going to have an effect. But in general, this principle of having two hidden states, one of which has a very sort of like direct line of influence in terms of backpropagation from downstream to upstream, is very useful, and is a kind of like, I don't know, like a common method for getting neural networks to train more. Like this looks like something that we have seen before in terms of like training very deep networks, and preserving the gradient through those. What's that example? Say it again? Yeah, resonance, exactly. Resonance. Resonance have these skip connections, or these residual connections that connect the input of these, two convolutional layers, this conv block here, the input to that to the output of it. So that when we do backpropagation, yes, there's all kinds of signal that's that's going through all these convolutional layers, but there, in the backpropagation, we can skip all of that over these skip connections. So there's always going to be signal there to use in adjusting the weights. If you remember how this was done, I actually wasn't here for this lecture, but I'm sure Ming-Jin showed you this. If you remember, this is just like a simple, the output of this plus this is equivalent to if we didn't have the skip connections. But adding them into the computation guide explicitly, sorry, explicitly, uh-oh, I should have some water with me, but I don't. Explicitly just allows for the computation to happen, or the backpropagation to happen, much better. So it's interesting, like it's equivalent, but in terms of like the computational properties, this is much better in terms of the backpropagation algorithm, and that's the same thing that's happening here. This track, or it's sometimes called a highway. This highway here is much more efficient in terms of backpropagating signal. Even though, like in some sense, you can think of it as like giving equivalent information. Although the gating does not make it equivalent. And there are things known as highway networks that are something in between. So they have things that look like skip connections, but they're gated, and they're keeping track of two states here, G and Y, and this internal state, is the thing that allows for the gradient to pass through. So highway networks never really made it to be like things that people used a lot, but it's in building up kind of the theory of why you'd want to do these things, or why these things work in the first place. They're very helpful. So LSTMs, sorry.
Where does the name long short-term memory come from? Why is it called that?
Well, so it's the ability to keep for a long time, to preserve for a long time the things the short-term memories that it's accumulating as it's seeing data. So one of the best ways to think about it is just that this allows for LSTMs and like variants of LSTMs allow for the recurrent neural network to accumulate meaningful state over much longer sequences. So you have this long-term memory, even though like at every step you're integrating like a short-term memory into it. So you can think of like the H's as being like the representation of like the short-term memory. That it's adjusting rapidly given the current and recent input, but that this is the C state is not adjusting so rapidly to preserve sort of like long range correlation. So what this practically allows you to do is to have much longer dependencies, right? So like if you're producing texts or maybe like translating, now you can translate much longer sentences from one language to another using all of that context than you could with like a plain vanilla RNN. Or if you wanted to produce text, like this can produce text where the next word not only depends on sort of like what it saw recently, in the presentation of the data to it, but like what it saw, paragraphs ago, for instance. And that what's good about that? Well, if this thing is like trying to produce coherent text, and it's trying to kind of keep track of, like a theme. It can't like forget about the theme 20 tokens in, right? It needs to remember that. And so like these kinds of architectures, you know, at least give the ability to have those correlations be on proper scales. Now, turns out that like transformers kind of blow this kind of stuff out of the water in terms of being able to do that kind of thing. But until we had transformers, this was like state of the art.
When did transformers come out?
2017. And no one really knew what to do with them until like, you know, a couple of years later, and then all of a sudden all the big labs had trained massive transformers, and all of a sudden you had the cool things like GPT-3 and the related, you know, the related models that are doing the amazing things that you see. And now the really cool things are like how people are, you know, taking these and you give you like write some words and it produces an image or even like a video that is semantically kind of correlated with that input. It's all allowed by transformers and the massive capability that they have to sort of like, you know, faithfully store and will just faithfully store like tons of correlative information from huge data sets. Okay, so one thing I was going to say, I think right before you asked, was just this could be the case without all this kind of weirdness about like gates and stuff like that. Like the why on the gates is not exactly the why of like, you know, why you want to have the second hidden state for like being able to preserve information and large gradients as you backpropagate through large computation graphs. It just so happens that like this is how it was done, seems to work well, and so people use it. There are variants of this. For example, here is a GRU, a gated recurrent unit, and it looks very similar. You know, again, it has this hidden input, or sorry, not hidden input. It has this input, the hidden state, and it produces. So you have this linear, you know, these linear operations. Again, it has like some gating information. So like you compress this down to sigmoids. You use those gates. The RT gate here on the hidden state. You use the ZT gate here on this hidden state. You can see there's kind of like a balanced, like convex combination between these two to give you the final hidden state. So it's a little bit different from an LSTM, but in practice it's like it's solving the same problem. It's, you know, it's giving you a you know, good gradient signal through the intermediate hidden states, and you know, whether you use an LSTM or GRU kind of like depends on, I don't know, if you like Schmidt-Huber or not. I don't know. They really perform pretty much the same. It's just that, like, you know, accidents of history, LSTM sort of caught on, and there's probably like some people who are like diehard, like, yeah, they're always better than GRUs, but they're basically the same. And you know, you mostly see LSTM, but every once in a while you see like a diehard GRU guy show up and like, hey, let's do GRUs, forget LSTMs. But you know, in spirit, they're pretty much the same. And there's lots of different ways you can do this. You know, they're all kind of, these are these different variants as well. They're all essentially solving the same problem with slightly different ways of doing this, and could give you different behavior on a particular data set or something like that, a particular task. But in general, most people just pull out the old LSTM, and if they're more modern, they're pulling out transformers these days. Okay, we're like actually done a little bit early. Surprising. All right, yeah. Yeah, I want to go back.
Yeah, I mean, looking at the year of publication, this came after AlexNet, and I still noticed that the
They came after what?
The AlexNet. So
everything came after AlexNet.
Yeah.
2012 starts everything.
Exactly.
Then all these things started. You know, they started to figure out.
The activation functions are still sigmoid and tangent and different values inside. Is there a particular?
So the sigmoids are there because of the interpretation of these as being gates, zeros and ones. That's why they're there. Like, why the tanh? This is like a really interesting. This is really interesting. It's because it's literally because the LSTM is old, and
right.
From 1997, right? And like used the tanh. No one was using ReLUs back then. The GRU is from 2014. I imagine that like they tried a ReLU or something like that, but like honestly, I have no idea. Like, I think it's just like it's a historical thing. It's like this is the way that you do these kinds of models, and I don't know enough about these. There's probably some good argument that I don't know about. That's like, well, if you do use a ReLU here, then you lose some blah 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 thing here, or I don't know. It performs weird here. Honestly, I don't really know. I think one of the other arguments for why you wouldn't want to do that, just kind of like, just thinking about it, is the way that these all work is that you have like this output and then you gate it, right? So the ReLU is already like a gate, right? It's like, if you're positive, great. If you're negative, you're not coming through, you're a 0. So you don't, like, you probably would work, but my guess is that like it would just put you in the linear range here of the ReLU in general, because like you'd want this gate to be the thing that decides whether you're 0 or not like this gate. And that's probably one of the reasons why. But of course it does promote things like, vanishing gradients and such, so don't have a good answer for you. It's part history, probably part more like, yeah, if we make some changes here, it makes it harder to interpret some of these things, and we don't want to do that. Good question though. I was wondering if someone's gonna like challenge me on that, because I told you like don't use sigmoids. And don't use sigmoids. Use transformers. Yeah. Okay. So summary. Bar ends. Pretty excellent models for sequential data, at least up until we found some other ones that benefit from just being able to train huge models. The plain vanilla RNNs that we mostly looked at, they're simple. They don't work very well because they have these gradient problems. We saw that you can kind of overcome that by adding an intermediate hidden state that doesn't have a matrix multiplication associated with it. So that's the case with LSTMs. This GRU we just looked at, that this all allows for this kind of like highway of information, so to speak. This doesn't control the exploding gradient problem. You still might need to clip. In fact, this is very common with LSTMs, is just to have clipping involved. And if you don't know yet, you go into your like optimizers and things like that for like in PyTorch, and there will be like an option built into it to like have clipping already. Like it's just a common thing, so it's built in to most frameworks. Yeah, and then we just don't use plain vanilla RNNs. You just don't use them. Like no one does it. Like really, like even worse than the Sigma. If you see somebody using a plain vanilla RNN, you just like, man, you're a noob, complete noob. What are you doing? So most people just pick up this, LSTM, or if they have some like reason, they might pick up a GRU. Yeah, and then there are other architectures, and in particular, we're looking at transformers these days. So next time we just talk about neural translation using like LSTMs, basically recurrent neural networks, and then so that'll be on Thursday, and then next week we start talking about transformers. So here to answer questions. Otherwise.